Fertilizers are crucial to supply the soil with new nutrients because of the nutrient loss from farm soils to the ocean. Many fertilizers contain phosphorus, a nutrient which is necessary for plant growth. Currently, phosphorus is obtained from mining phosphate rock, but phosphate rock is a diminishing global resource. Petroleum deposits are diminishing globally as well. The implication is that an agricultural system which depends on inputs that are non-renewable, such as petroleum and phosphate rock, is not sustainable. The third problem of modern agriculture is the negative implications that it has on biodiversity. 1/3 of all the land on the world has been converted into agricultural land, for example through deforestation. This trend has led to a huge loss of natural habitat. The constant flow of nutrients from the soil to the ocean causes large algal blooms in many water bodies. These new conditions cause a decrease in biodiversity. Of the around 3,000 edible plant species, we only produce around 35 high-yielding varieties, some of them GMOs, often on large-scale monoculture farms. This practice strongly disfavors biodiversity. The use of pesticides also harms biodiversity. The widespread disappearance of bee colonies all around the world, for example, is largely attributed to the harmful effects of pesticides. All this shows that the activities of modern agriculture damage the ecological balance and threaten biodiversity.
So what can we do to produce our food in a sustainable way that benefits biodiversity and does not dependent on non-renewable resources? Our correspondent has visited an organic farm in Clearwater Bay in Hong Kong searching for answers.
For the plants, how can you let them to get enough nutrient without using some chemical fertilizer?
We collect horse manure from the stables and it's mixed with hay and some wood blocks and we compost it on site here.
May I ask, how can you prevent your crops from pests?
We create biodiversity, we plant many different plants and we create a mini ecosystem. So within that ecosystem comes resilience.
This means that the sustainability of agriculture can be promoted by growing diverse plants to support ecosystem resilience and by producing fertilizers locally from manure and other organic inputs.
We hope that this report has provided you with some insights into the problem and possible solution for modern food supply.
And we look forward to seeing you again soon. There are still many environmental issues out there to be addressed.
and in return they get nutritious honeydew. When species get dependent like this in the natural world, over time they tend to change very, very rapidly indeed. For example, the ants after a time get so dependent on the aphids that if all the aphids died, the ants would starve to death. And the aphids get so dependent that they cannot reproduce without the honeypot ants. Biologists refer to such relations between species, such relations of close dependency, as symbiosis. But when humans are involved in such relations, we tend to call it farming or agriculture. When humans started farming, the species they tended to began to change quite dramatically. This was because humans selected the most nutritious wheat grains or rice grains or corn grains, or the most docile and fattest animals. And the result was that within a few generations, new domesticated species began to appear, and they were created not by natural selection, but by artificial selection. You can see the difference very, very clearly if you can compare a modern corn cob, which is fat and nutritious and tasty, with its ancestor Teosinte, which is a rather pathetic looking weedy plant. Or if you compare a modern sheep, domesticated sheep, which tends to be fat and docile and frankly not too smart, with its ancestor, a mountain goat, a very intelligent, athletic creature. Humans changed too, but they tended not to change genetically so much as technologically, socially, and culturally. They learned to clear trees, to build paddy fields like this, to divert rivers, to protect their crops and animals from pests such as rats or wolves. And the result of all of this was that humans found that they could produce more of what they wanted from a given area, from a small area, than they had before. And that meant that humans could now live in sedentary villages rather than being nomadic. But to get a real sense of what's going on with farming, we need to think about it from a big history perspective. Remember, all the energy that supports the biosphere, or most of it, comes from sunlight through photosynthesis. So what farmers were really doing was diverting more of that energy into species that they could use and away from other species. The result was a sort of huge energy grab by one species, our own. No wonder, with farming, human populations began to grow so rapidly. So, where and when did farming and agriculture begin? At the moment, it looks as if farming really began about 11,000 years ago in the highlands east of the Mediterranean that we know as the Fertile Crescent, and here they grew wheat. It may also have appeared at about the same time in the Nile Valley, slightly further south. Then, from about 8,000 years ago, we have evidence of rice growing in China, and at about the same time, we have evidence of the growing of taro and yams in the highlands of Papua New Guinea, though it took several thousand years for agriculture to really flourish here. Then, from about 5,000 to 4,000 years ago, agriculture pops up in several different parts of the world. In West Africa, farmers start growing sorghum and millet, and farming also appears in the Americas, right across the Atlantic, in Mesoamerica, where they're growing maize and squash, and also in the Andes, where potatoes are a very important crop. From these core regions, agriculture then spreads to neighboring regions. But there's a real puzzle here, because none of the core regions seem to have been connected. So what was really going on? So why, after almost 200,000 years of living as foragers, did humans in so many parts of the world that had no connection between each other begin to behave in such similar ways in such a brief period of time? Well, there seem to be two main reasons. One factor is overpopulation, the other is climate change, and these factors operated in many different parts of the world. Let's take overpopulation first. During the Paleolithic era, if populations grew too much, you could generally solve the problem by migrating into a new region. But after the settlement of the Americas from about 15,000 years ago, there were no large areas left to migrate into. So from now on, if populations began to grow, you had to try to get more resources from a given area. In other words, you had to farm. Now, that's the first factor. The second, climate change, is subtler. Most of the Paleolithic era was dominated by the Ice Ages. And during the Ice Ages, for the most part, climates were so cold and so unpredictable that farming was more or less impossible. Then, from about 18,000 years ago, global climates began to change. They began to get warmer. Glaciers began to retreat, sea levels began to rise, and in area after area, you began to get warmer and wetter climates. There was a brief period between 13,000 and 12,000 years ago when climates were cold again, but then from about 12,000 years ago, climates became warmer and wetter, and we entered the interglacial period that we're still living in today. Now, as a result of global climate change, humans and animals and plants everywhere in the world had to start changing their behaviors. In some areas, such as the Fertile Crescent east of the Mediterranean, as climates changed, resources became more abundant. There were more plants and more animals. And in these regions, these particularly favoured regions, some foragers began to settle down because they found they could live in one place for most of the year without travelling around. And they began to form villages. They became sedentary. In the Fertile Crescent, archaeologists refer to the people who settled in these villages as Natufians, and they've excavated many of their villages. But as they settled down, their behaviours changed, and in particular, populations began to grow. We're not sure why, but one reason may be that if you're a villager, you don't have to carry children around, so there's less pressure to reduce the number of children. In any case, populations grew, and that posed a problem. Within a few generations, they found they didn't have enough resources to feed everyone in what had once seemed an area of abundance. So what are they to do? Well, perhaps they could go back to foraging. The problem was they'd probably forgotten many of the old techniques of foraging, and besides, neighbours probably occupied those lands now. So what can they do? Well, they can start tending their crops and animals more carefully. They can start providing the plants they like with extra water. They can start clearing away weeds. They can start penning particular animals in enclosures. In fact, they can start farming. Now, something like what happened to the Natufians seems to have happened in many other areas. In the case of the Natufians, we have lots of evidence about this expansion of villages and population growth. But something like this happened in many areas, and everywhere the same two factors seem to have been involved. First, global climate change, which made agriculture possible, and secondly, overpopulation, which made it necessary. Agriculture is our seventh major threshold of increasing complexity. As we've seen, these are pivotal events that allow the creation of new, more complex things with new emergent properties. Agriculture is not just a matter of tastier fruit or fatter cows. Agriculture unlocked forces much more powerful than that, and they would transform human history. How and why?
Fields to teach students. We have plans to do research, and we also have demonstration of horticulture equipments and activities. We organize trainings for different people. The easiest is to train the students. Then we do a lot of training of the trainers from all over the countries. We also train farmers. We have trained the people who come to visit our agricultural fair every year. Well, CoolBot is a simple control system that fools the air conditioning. It has a small heater to keep heating the temperature sensors of normal air conditioning. Normally, when the temperature gets to a certain point, the thermostat will kick in and stop the power. In order to keep the temperature lower than normal 20 degrees Celsius, we use the CoolBot to heat the temperature sensor of the air conditioning and fool it. And then we can set it to 10 degrees Celsius or even 1 degree Celsius. I guess more than 50% of the normal commercial home air conditioning unit can be modified using the CoolBot.
I'm familiar to vegetable and seed production, right? So I'm thinking CoolBot can be a good choice for smallholder to store their fresh vegetables. And if we apply dehumidifier inside the cupboard, it can be a big container to store the seed also.
Cool chain can improve the shelf life of vegetables and produce. Definitely can even double it, but the quality that we can maintain using the cool chain, I think it's the most important thing. In Asia, we lose a large percentage of produce through post-harvest loss, and the loss is not just the quantity loss. The biggest loss is the quality loss, the loss of vitamins and minerals. And then we will have the problems of food safety, the contamination. I think when we quantified it, it's really worth it to invest in cool chain. There are two types of solar dryers. One is the FAO recommended type, and the other one is excellent idea, solar dryer. It's produced by the Professor Michael Reed from UC Davis. It simply add a chimney to it, and it creates airflow that would work very well, especially in Thailand and in the hot, humid, because the humidity inside the system can be very high. You need to find a way to vent it out. The system is really nice, I believe. You can use wood, you can use bamboo, PVC, whatever you like. So it's really flexible. The solar pump is very simple. It's a 12 volts or 24 volts pump. It can be connected to the solar cells that produce electricity. Or if you want the pumps to work at night, you can install the batteries. Rainfall in the tropics doesn't come every day, but the plants needs water every day. So water must be there. The system of the solar power irrigation can be linked to the drip irrigation system. This is one of the best combination because we know that the drip irrigation saves a lot of water.
These technologies, one thing is very much common among them is the low cost and indigenous knowledge. They can be repaired in-house, they can be maintained by the local artisans. So this is very good. And the cost is relatively low, lower than their competent alternative products. $300, if you'll ask a small farmer, will he or she be able to invest? The answer is quite likely yes, because the amount of saving these farmers can make is very good. And that is the decision-making point for the farmers in favor of adopting these small technologies.
A lot of things can be done with a small investment, with innovations, in order to help the farmers so that they can live better life.
Agricultural pollution will likely accelerate changes in agricultural production. This will be a challenge for farmers across the globe. In addition, in many geographic areas, farmers will be challenged with significant changes in climate.
In this lesson on adaptation to climate change, we will be discussing both reactive adaptation and anticipatory adaptation. Reactive adaptation refers to the short-term adjustments that farmers make in response to current climate conditions. Anticipatory adaptation includes any long-term planning and changes made as a result of predicted climate changes. Both are important.
And farmers are already adapting. So you see farmers that are planting earlier, that are relying on larger equipment to be able to get into the field quicker because their planting windows are shorter and their seasons, springs in particular, have been wet across the Midwest and Northeast. We've seen farmers that are going back and installing more tile drainage and increasing drainage to deal with these wet conditions. And so while we're seeing changes in climate, we're also seeing farmers adapt to what they're seeing on the ground. Now that adaptation has been reactive. Farmers are responding to what they're seeing on the ground, what they've seen over the last 3 to 5 seasons, and trying to plan accordingly. And that's working for now. But as we look forward, we're going to see an acceleration of climate change. That's what all of the analysis is showing, is that the trends that we've been seeing, which have been about 0.2 degrees of warming per decade, we expect that to increase over the next century, where by the middle of the century we could be seeing 0.6 to 0.8 degrees of warming per decade. And at that point, farmers are going to have trouble keeping up if we just rely on reactive adaptation.
We will be discussing adaptation strategies, reactive and anticipatory, through the lens of a climate audit. We will divide the farm into 4 segments to help organize the audit. They are farm inputs, animal production, logistics, and farm exports. Some adaptation strategies may be short-term and will affect the farm's current management practices and decisions. Long-term adaptation strategies include things like investing in genetics, buildings, or equipment, or diversifying the farm. Making decisions about which adaptation strategies to implement requires data. Unfortunately, the data on future climate conditions is uncertain, and that can make decisions on whether to invest in long-term strategies more complicated as farmers weigh the cost of investing against the potential benefits.
Farmers are always looking for ways to cut their costs and ensure their profitability, and this would be no different than any other kind of technology that they would sit down and say, okay, I'm losing X number of sows that we're going to attribute to heat stress, and that's costing me Y dollars per year. If I put some kind of mitigation strategy in, whether it's a geothermal or whether it's just air source heat pump or something, and that system's going to cost me X, and it's going to cost me so much to manage it and keep it operating, and they'll do the math and say it'll pay back in 35 years. Nah, I'll wear the cost of the lost sows. If it's going to pay back in 3 or 4 or whatever their break point is, they'll say, yeah, we'll have a go at it, and then technology will get better and it'll pay back quicker.
The farm audit begins with farm inputs. We will look at ways to reduce the exposure of these farm inputs to the risk of climate uncertainty. These inputs include water, feed, energy, young stock shipped onto the farm, and other farm supplies. Climate adaptation is also referred to as building of climate resilience, reducing climate vulnerability, or reducing climate risks. Reducing climate risks for the important farm inputs of feed and water will mean something different to farmers who grow their own feed versus those who purchase feed. It means something different for farmers who pump water from an aquifer than it does for those who get it from a river sourced by snowmelt. It may also be of greater concern for some than others, depending on local climate trends or climate projections. Many farmers are already adapting their feed systems to become more resilient. They are making changes in crop rotations, crop genetics, or in forage and pasture management.
I think that what is probably helping to reduce the effects of these changes are the way that we're managing the animals, managing the grazing. I'm using a planned grazing process where it's high density, short duration grazing. And so even when we get into those periods where we're having a summer, a drier summer, for instance, that we're able to get through that because of the planning process and because we're able to produce more forage. Because I know that there are going to be times when maybe I am going to have to sell animals if I don't have enough feed.
One of the most critical points is to manage stocking rates to match the pasture availability in natural grazing systems. If you don't do that, you end up overgrazing and you get longer term degradation so that you get damage to the environment. And that's not helpful to the farmers in the long term in terms of income, but it's also not helpful to the environment. So the recommendations that we can make are to manage in advance for your stocking numbers, the number of animals that you hold relative to feed, to feed early, so to down stock early and to feed early. That's not, that's easy to say, but it's not easy to do in terms of feed costs and the capacity to offload animals. But that's the first recommendation. The second recommendation is to look to the future at how you can improve your grazing systems to be more drought tolerant in the species that you might sow into your pastures.
So those who can be proactive and get up on the early side of the drought and have that flexibility in their system to make management decisions ahead of time before that drought really becomes an economic devastation to the enterprise.
A lot of ways that individual producers try to prepare themselves better for drought is to improve the monitoring on their farm.
If we can improve soil health, improve organic matter in the soils, they turn out to be more resilient to extremes, both extremely wet conditions and extremely dry conditions. And so soil health is going to be a key part of our strategy going forward. Genetics is another important strategy. We've seen improvements in the crops that we've grown over time, and that's resulted in improved productivity, but it also has resulted in crops being more resilient to things like drought. And so the crops we have today that we're working with, the soybean and corn crop in particular, is a stronger crop with stronger root systems, deeper root systems, and those plants are more likely to withstand drought than even the crops we had 20 years ago.
One farm in South Dakota recently made news headlines with its comprehensive adaptation strategy to survive drought. This 5-point strategy involved adding more forage reserve, both standing and stored, managed grazing to build resilience in soils and grasses, storing more hay to supplement forage, monitoring rainfall and soil moisture, adjusting animal numbers after anticipating the future forage supply. Other short-term adaptations for farm inputs in areas prone to drought might include more efficient crop irrigation or planting drought-tolerant crops, better soil management to enhance water retention, additional capacity in stock tanks or farm ponds, integrated pest management programs, since climate change can cause new disease and weed problems for crops, additional feed suppliers or more feed storage on the farm, multiple suppliers of young stock. Increasing the farm building's resilience may require additional fuel storage or additional backup electrical generation if the farm's energy supply, fuels, or electricity are vulnerable. Long-term adaptation strategies for farm inputs should also be considered. Ensuring an adequate feed supply might require more extensive pasture or rangeland improvements. It may require changing crops or tillage to better match climate conditions. Water security may mean drilling new wells, installing new irrigation systems, expanding farm ponds, or purchasing water rights. Long-term adaptation might even include moving animals to other geographic regions with a better water supply. The animal production phase of the farm operation is also quite vulnerable to climate changes. Often, this vulnerability might show up in the form of heat stress on the animals. Heat stress may impact production and reproduction, and can also increase the risk of diseases and other animal health concerns. Short-term adaptation strategies to prevent heat stress in animal production should include more monitoring and better management of existing systems, making sure the ventilation system is working properly, adjusting temperature set points, monitoring animal behavior for signs of heat stress, making sure animal cooling systems are operational in the early spring and late fall, improved protocols for feeding in hot and cold weather, adding more watering locations, shade structures, or other heat abatement systems. Many of the short-term adaptation strategies for heat stress just described are already deployed on most farms. Proper cooling requires protection from the sun with either shading or building, followed by good air exchanges in any buildings and adequate air speed across the animals. Proper cooling also includes misting systems or soaker systems for animals that lose heat through evaporative cooling. It is also important to focus cooling strategies on areas such as the holding areas in dairies or wherever animal density is greatest. Farmers and animal production experts can describe the many benefits of implementing these short-term adaptation strategies for heat stress.
I would say spray cooling is probably the most common. One of the advantages of it, especially in loose housing where cows are feeding at a common feed area, is that's where the spray cooling would be. It would soak them, and usually it's a cycle of anywhere from 5 to 10 minutes. They'd soak them for 1 to 2 minutes, and then it would evaporate for the rest of the period.
For our sow farms, we have a cool cell system, which essentially is It's a filter before the air comes into the barn, and cool water comes down to it. We can drop temperatures about 10 degrees at best from outside temperature. So for grill finishing, we're naturally ventilated, which we're counting on the wind. We're counting on outside temperature. We do have a mister system to replicate sweating for pigs. That won't go on until about 85 degrees. And we turn it on for about 10 minutes, and then we turn it off for about 20 minutes, or as long as it takes to evaporate everything, so you don't soak the pigs the whole time.
They'll stand up and try to get more airflow across them, so you'll see a lot more animals standing. Rumination will actually go down. You'll actually get a decrease in activity, so even though they're standing, they won't be walking around as much. They'll try to stand in one spot. And so all of these behavioral changes, not only can you pick them up and they have economic losses to the farm from a production standpoint, but with some of the technologies that we have today, we can identify these behavioral changes and then hopefully go in and make changes at the farm level to cool the animal or alleviate some of that stress. If I can pick up that this animal is starting to become heat stress, and I can find out when that is and start cooling at that time point or wherever that is on the farm, then once I'm visually able to see a cow open mouth panting and saliva, the heat stress has occurred. The damage is done, right? So I want to be able to go in and try to start cooling and prevent that animal from getting elevated temperature and prevent her going into stress. Because once you can visually see it, most of the time milk production and the other switches physiologically have already occurred. And so that's some of the challenges, is trying to identify heat stress before it happens. I think the other thing is, and I run into this a fair amount, people that have a lot of cooling put in, but they get so busy. There's so many things going on coming to spring with farming and school activities, to you name it. And so I'll go to a farm that has a ton of cooling technology, but they didn't clean the fans, or a third of the fans aren't working. And the shades on the side of the barn, half of them are still up because they forgot to pull them down to allow the airflow to come through. Or, you know, you look at the nozzle heads on the sprayers, and, you know, a third of those aren't working. So, I encourage the guys, make sure and just do a heat stress audit on your farm. Make sure everything's working, everything's clean, your nozzles are working and stuff well before summer hits. Don't wait till summer hits to go out there and start making the changes, because once this animal experiences heat stress, again, talking about damaging the eggs, and you'll see the effects for a month and a half, 2 months. Once the heat stress occurs, it's hard to recover from that. So catch it before the heat stress occurs, and cooling those animals at the very beginning, well before summer. Keep in mind, animals are comfortable at about 40 degrees. Lactating dairy cows are about 40 degrees.
A lot of our farms, the calves are raised in hutches, and we've had some challenges just of the hutches getting too warm. So making some of those adaptations where we can lift up the back end of the hutch, or we've had farms where they've cut out the back of the hutch completely and put a hog panel in there just to increase the airflow.
Long-term adaptation strategies for animal production can include continual planning and large-scale investments in animal genetics, farm buildings, and pasture systems. As one example, dairy farms in the Midwest are moving away from naturally ventilated barns to mechanically ventilated barns, which give animal producers better control over the environmental conditions inside the barn.
When we originally built these barns, they were to be naturally ventilated barns, but we didn't do it right. We built them in a little bit of a valley instead of on top of a hill where you get the nice breezes, and they aren't really tall enough. You need at least a 16-foot sidewall. These are only 12, so we were having problems with cows in the weather like we've had this past week. They'd bomb, they'd just drop 7 pounds of milk in 2 days because they just weren't eating anymore. They were just fighting the hot weather. And so I went out to South Dakota and looked at the cross-ventilated barns that were going in out there, and I said, well, this is how we can salvage these barns and continue to use them. So we made them cross-ventilated barns. When we put the cross-ventilation system in there, the soaker lines were controlled by a thermostat, and they just never came on again, so we don't use the soaker lines anymore. We just depend upon the air movement through the barns to keep the cattle comfortable. I knew what it cost us to cross-ventilate these 2 barns, knew what kind of milk we were getting out of these cows. And according to my calculations, it was paid for in about a year and a half.
Geothermal cooling systems, like this one in western Minnesota, are also being considered by some producers as a viable long-term investment for animal cooling.
The real problem, primarily from production or environment or weather, is summer. And we can get very warm temperatures, especially this part of Minnesota. So providing some way to provide cooling, like a geothermal system, is, I think, things that we'll start to see being investigated more. And in this particular case, they decided to invest in these facilities on a more permanent basis, just because of their business model that they're using here, which is different than you're going to see in most production facilities. This is a 900 sow facility, farrow to nursery site. They're incorporating the geothermal system, and I think which is reasonable in a production system like this. It has to be integrated properly into the ventilation system, and the system basically has to be probably sized to provide sufficient cooling that you can also but still properly ventilate the facility. Even though you can't see them, there are 360 wells that are approximately 220 feet deep, kind of all around this first facility. You can see each one of these little openings or inlets on the side of the building. Each one of those, there are 36 wells that service one of those openings, and that acts as the inlet and thus the way that they temper the incoming air. So the investment made is kind of can be thought of as controlling some of the risk, preventing some of the catastrophic losses that might occur from real extreme heat conditions, which would not only result in loss of gain or production, but might result in mortalities.
Producers are also making long-term investments in animal genetics, developing breeds that are more adaptable to future climate conditions.
The other thing that farmers are managing to do is to choose breeds more carefully that respond better to drier, hotter conditions.
A recent study of breed allocation in Texas beef cattle showed that heat-tolerant breeds such as Brahman are growing more prevalent in the warmer parts of Texas. Another category of farm operation that is vulnerable to climate change is farm logistics. This category covers a wide range of farm management practices, planning decisions, and technologies. In the short term, there are many strategies to consider to reduce the vulnerability of farm logistics to climate events. These include being prepared with backup power for critical functions around the farm, forming emergency response plans in case of extreme weather events, making sure ventilation and cooling systems are ready early and late in the season, storing additional feed for times of drought or flooding, developing plans for transporting animals in extreme heat, planning for the transporting of supplies into the farm or exporting off the farm when there is flooding, planning ahead for managing animals in extreme cold or blizzard conditions, building resiliency into the manure management system.
Really, your manure storage is something that you should be managing all the time. You know, do you have a field that it is appropriate to apply it? Is there a period of time when you need to apply it in preparation for a period that you can't apply? And so no matter how big your storage is, even if you have a 1-year storage or more, you really need to be looking all the time for appropriate places to apply it and keep managing it.
Building resilience into the manure storage system also means setting aside higher, drier ground for manure application or managing the manure storage so there is room in case of an unexpected large rainfall event. A producer with a 5,000-head beef feedlot in southwest Minnesota had given up on fighting the weather and decided to move most of his animals into a barn with slatted floors and a deep pit for manure storage. He determined that the added investment was profitable in the long run based on labor costs and animal performance. The final phase of the farm operation affected by climate change is farm exports. Unfortunately, farmers do not have much control over the market prices for their products. Natural economic cycles of supply and demand, as well as local and national economics, all play a role and are all impacted by climate and weather. In the short term, practices such as contracting for farm products is common. Farmers also participate in insurance programs to protect against farm losses. These tools may become more important in the future, and they may evolve as a result of climate and weather changes. Many farms are already more diversified in products, vertically integrated, or have farms in several geographic locations to hedge against climate uncertainty. Unfortunately, there is no simple way to determine the long-term benefits of some adaptation strategies due to the uncertainty of future weather events and of future climate impacts on the farm. For instance, it's likely animal scientists do not yet completely understand the full impact of heat stress on dairy cows. So how can one possibly quantify potential damage from heat stress and weigh that against the potential benefit of a heat abatement system? Long-term adaptation strategies are also more challenging, as these investment decisions must take into account economic outlooks that project 15, 20, or 30 years in the future. Climate predictions are uncertain, as are population numbers, consumer demands, and global markets. Because of the uncertainty involved in making these long-term investment decisions, farmers should consult with a team of experts in a variety of fields that look at all aspects of a farm's operation. These decisions